Okay, so yesterday I solved up to 2019. Okay, we are solving past papers from the chapter of metallurgy, and we've solved up to 2019. So today I'll continue with 2018 paper. Okay, since I'm not going to display the questions, I'll only read out because displaying will take longer time. So I want you to sit with your book, and as I give you the answers to the question, just follow the questions from the book itself. Okay, so the questions won't be displayed here, only the answers. Okay, so first one, 2018. First one is, give a reason for alkali metals. Give a reason for alkali metals are good reducing agent. So alkali metals are metals of first group of the periodic table. They are lithium, then sodium, and then what else you have? Potassium, you know, and then rubidium and cesium and francium. These metals from the first group of the periodic table are called alkali metals. Okay, so they are good reducing agent. Why metals are reducing agent, by the way? Because how do metals react? Metals react by losing electrons. For example, these alkali metals, their valency is 1, so all of them lose electrons. Okay, and then after losing electron, they become positively charged. Like lithium becomes lithium plus ion, sodium becomes sodium plus ion. So they lose electron and then they become charged, or they form positive ions. The process of losing electron is called oxidation. So these metals, by losing electron, themselves gets oxidized. And if they themselves gets oxidized, what do? They cause reduction in others, because they themselves are getting oxidized, you see. So they will cause reduction in others. That's why metals are always considered as a reducing agent. But among the metals also, the alkali metals, there are metals like iron, chromium, and aluminium. But compared to these metals, alkali metals are considered as a very good reducing agent. Didn't we discuss this last time? We did. You remember when we discussed this, when we planned for the extraction of metals, we placed metals according to their reactivity as per metal reactivity series. Like potassium is at the top of the series, and then sodium, then magnesium, then calcium, then magnesium. So this is how we arrange the metals downward. Okay, so there what do you find? You find potassium and sodium at the top of the metal activity series. Why? Because they are very good metals, and being a very good metal, what do? They lose electron and they easily get oxidized and acts as a strong reducing agent. Okay, so alkali metals are good reducing agents because they have very good ability to lose electron. I think in the chapter of periodic table, you may also have read about ionization potential or ionization energy. Alkali metals have very low ionization energy. That means the energy required to lose electron is very less. So with little bit of energy available from the surrounding, they lose electrons, and because of that, they get themselves very easily oxidized and therefore act as a strong reducing agent. Okay, so the basic reason why alkali metals are good reducing agent is that their ionization energy is low, they tend to lose electron very easily, and therefore they act as a strong reducing agent. Okay, so second question from 2018. In the meantime, let me add some pages. Yeah. So second one we are solving now from 2018. Okay. Give one word or phrase for the statement. The process by which sulfide ores are concentrated. Sulfide ores are extremely light ores. So what is the process by which they are purified or concentrated? The answer is froth flotation, isn't it? So that's the answer. This everyone knows. So third one, fill in the blank with the correct choices given in the bracket. The most common ore of iron is, the most common ore, last time we've written this, most common ore of iron is which one? Hematite, isn't it? So hematite is the ore. That's the answer. Everyone knows this. And next one, that's number 3. Fill in the blank with the correct choices given in the bracket. Oh, that one we did. Number 3 we did. Number 4. Name the main component of the alloy. There are alloys given, brass and duralumin. So the main component of brass. Alloys are mixtures of metals. So these metals are, so they have certain metals mixed together. Brass is a mixture of which metals? It is a mixture of zinc and copper. So the main component of brass are zinc and copper. And then next, duralumin. Duralumin has one of the metal, I think you must be knowing, no? Duralumin. Yesterday we talked about the composition of duralumin. At least I mentioned one of the metal present there, which is extremely light metal, and that is aluminium. One of the component is aluminium. The other component is magnesium. Okay, now next one. That is number 6 from 2018, okay? Number 6 from 2018. Name the process by which... Oh, no. Number 6, number 5, though I haven't done. Okay, number 5. Sorry. Come on. Number 5. The 2 5s. Actually, I counted brass and duralumin. Both were number 4. But then I considered duralumin as 5. So it doesn't matter. 5th question now. Name the most common ore of metal aluminium from which the metal is extracted. So main ore of aluminium. You already know. We have already discussed the extraction of aluminium from its ore. So what is the ore? It is bauxite. And you should also know the formula of bauxite ore, which I think everyone knows. It's Al2O3 with 2 water of crystallization. Then the number 6 question. Okay. So what is there in number 6? Name the process by which the impure ore of aluminium gets purified. Oh yeah, impure ore of aluminium. Aluminium oxide is amphoteric. Aluminium is an amphoteric metal, and its ore is purified by this leaching process. And what is the name of the leaching process by which the bauxite ore is purified? It is known as Bayer's process. So I think you know this already. Bayer's process. In fact, you should know almost everything over here. We have discussed almost everything, whatever is coming up. Write a balanced chemical equation for the number 7, okay? Write the balanced chemical equation for the formation of aluminium at cathode during the electrolysis of alumina. So last time, yesterday when we discussed the extraction of aluminium, you have written those electrochemical reaction, no? Reaction occurring at anode, reaction occurring at cathode. So they want us to write the balance equation for the extraction of aluminium, but the reaction only at the cathode, okay? For the formation of aluminium at the cathode. So the at cathode means cathode is which electrode? Cathode is negative electrode, isn't it? So which ion goes there? Aluminium ion goes there because aluminium is positive, and it gains electrons. How many? 3, because the valency of aluminium is 3. Aluminium has +3 charge, and after gaining electron, it becomes neutral atom of aluminium. This is how aluminium is extracted. So this is the reaction that is extracted, that is involved in the extraction of aluminium at cathode. Okay? Yeah. Okay, one more page, let me add. So next one, we are still continuing number 7 only from 2018. Number 7, there's another part of it. Action of heat on aluminium hydroxide. Action of heat on aluminium hydroxide. Have you ever done this one? Have you ever heated aluminum hydroxide or studied this reaction? We did this in the Bayes process itself. You remember, in the last step of Bayes process where we purify bauxite ore, what happens? Aluminum hydroxide is formed by the salt hydrolysis of sodium aluminate, and that aluminum hydroxide is insoluble. So we just filter out, and then what we do, we heat that at 1100 degrees Celsius. And when hydroxides are heated, you know what happens? It always forms oxide, aluminum oxide, and it also liberates water. So we are supposed to write a balance equation for heating of aluminum hydroxide or action of heat on aluminum hydroxide. So you know aluminum hydroxide, like every hydroxide on heating, breaks to form oxide and water. Now balance this. On the right hand side, you see you've got 2 aluminum, isn't it? So how do you balance this? By writing 2 in front here. So let me write 2 there. Okay, oxygen is aluminum is balanced. Now how many hydrogen atoms you've got on the left here? You've got 6, no? 3 to the 6. So how do you make 6 hydrogen on right hand side? By simply writing 3 in front of hydrogen. So if you write 3 over here, 3 to the 6. So now the equation is balanced. Even the oxygen atoms are balanced. You see, you have 3 oxygen here and 3 oxygen there. That amounts to 6 oxygen, and we already have 6 oxygen on left hand side. So that's the balance equation showing what happens to aluminum hydroxide when it is heated. Okay. With that, we completed discussing 2018. Now we'll move to 2017. So now 2017, let me write that with a different color. Okay, 2017. 2017. Okay. So 2017. First one. What do you have? From the list of terms given, choose the most appropriate term to match the given description. So you have certain terms, and then there are certain processes. So you've got to match the term with whatever is being described. Okay, so first number 1, what is there? Crushing of ore into fine powder. Every time before we start purifying ore, what do? We crush ore, we powder that ore. What is that powdering process known as? It is known as pulverization. Pulverization. So pulverization is nothing but crushing of ores or turning ores into powder. Okay, and this we always do before purifying ore, before the concentration of ore. Okay, number 2 is also there. Heating of ore in absence of air to high temperature. When we heat ore at high temperature without oxygen, what are we doing actually? It's a preliminary treatment called calcination, isn't it? So all these we discussed last time. It is something which we have already completed. So we are continuing 2017. Number 2 question now. Name the following: an alloy of lead and tin that is used in electrical circuit. Yesterday only I told you there's one particular alloy which is used in electrical circuit, in electrical fuse. And why do we use? Because we want to protect the circuit from catching fire when it gets overheated. So we need a metal which is a good conductor but has a low melting point, and for that we use which alloy? Solder alloy, isn't it? And what makes this alloy? Alloys are mixtures of metals. So solder alloy is actually made up of 2 metals mixed together, lead and tin. So you can memorize also the composition of solder alloy. In fact, I want you to, you have some tables given in your books, no? So table where properties of alloy, composition of alloy, and the uses are all given. So I want you to go through those important ones. But as it comes in the question, I will be telling you also. So solder alloy is the alloy used in electrical circuit as fuse because of low melting point and good conductance. It is made up of lead and tin. Next, an ore of zinc containing its sulfide. Yeah, remember last time we have written so many sulfide ores. What were those? Z and S, zinc sulfide. It is also called zinc blende, isn't it? We call this zinc blende. And PBS, remember, that was galena. You have written all this in your copy. And then copper pyrites, COS, copper pyrites. So all these important sulfide ores I have given you. So this time they are asked for what? A zinc sulfide ore. And that is nothing but zinc blend. This is the one. Okay. Let me add one more page. Let me add many pages on this time. Let me add many pages. More pages. More pages. Okay. Now what is next? We are continuing 2017 paper. Okay. Now, number 2 question. What is that? Name the following. An alloy of lead and tin that is used in. Oh, yeah, we finished this one. Sorry. The last part of number 2. Last part. A metal oxide that can be reduced by hydrogen. A metal oxide that can be reduced by hydrogen. You remember when we planned for extraction of metals, what we discussed was the metals which are at the top of the metal activity series like potassium, sodium, coming up to aluminum are highly electropositive. They themselves are very good reducing metals. So their ores cannot be reduced by simple chemical reducing substance. So that's why they were extracted by electrolytic reduction method, and one of the electrolytic reduction we have already discussed also in the extraction of aluminium. And below aluminium we had some metals like zinc and iron, and we name these metals as moderately electropositive metals. They are not highly reactive, moderately electropositive, isn't it? And if you have oxide ore, if zinc ore is zinc oxide, if iron ore is iron oxide, then we said that, means I said that you can reduce them either by hydrogen, okay, or by carbon, or by carbon monoxide, and the name of the process was carbon reduction process, isn't it? So that's what they are asking. You got to name a metal oxide which can be reduced by hydrogen. So you can take any metal oxide below aluminium. You can say zinc oxide, iron oxide, or copper oxide. Yesterday we even discussed this reduction of copper oxide. Remember, copper oxide is black in color, I said, and then if you heat that with hydrogen, hydrogen reduces that to form copper, and then itself get oxidized. So you can give any example. This one is also good enough, this reduction of copper oxide. So you can name any metal oxide which can be reduced by hydrogen. I think copper oxide will be best. Then comes what? Then the number 3. Answer the following question with respect to the electrolytic process. Answer the following questions with respect to the electrolytic process in the extraction of aluminium. Okay. Identify the components of electrolyte other than pure alumina. In the extraction of aluminium, we don't use pure alumina for so many reasons. You have written down those reasons. We add a lot of impurities to alumina and we take a mixture of electrolytes. So identify the components of the electrolyte other than alumina. So we already have alumina in the extraction of aluminum, but what are the other things that you have to identify? One of the most important things we add is cryolite, Na3Al F6. And we also add fluorspar, isn't it? So which are the components that you have to identify other than alumina that goes in the extraction of aluminum? These two. So you've got to say one of them is cryolite, another is fluorspar. Got it? That's the answer. And you got to write the role played by them also. So role also yesterday only we have written. You remember? What is the role of Na3Al F6, that is cryolite? The role of the cryolite is to lower the melting point from how much? 2050 to 950, isn't it? And to improve the conductance. What is the role of calcium fluoride? To decrease the viscosity, isn't it? These things you have written. Decrease the viscosity or increase the conductance. That's it. So the role of both these components I have already mentioned in the previous class. Okay, good. Then what else we have? Explain why powdered coke is sprinkled. Now I'm not going to repeat this. Why powdered coke is sprinkled, you study from the copy. Okay. So whatever is there in the copy, whatever you have already taken on, why should I repeat? So you just copy, read it from the copy. Okay. Next, number 4 of 2017. Number 4 of 2017. What is that? Complete the following by selecting the correct option from the choices given. The metal whose oxide, which is amphoteric, metal oxide, which is amphoteric, is aluminium oxide, aluminum metal. The metal whose oxide is amphoteric is reduced to metal by carbon reduction process. Oh. You know, they are talking about a metal, okay, whose oxide can be reduced by carbon reduction process. So it can't be aluminium. Aluminium oxide we don't reduce by carbon, we reduce by electrolytic process, even though aluminium oxide is also amphoteric. So we've got to think of some other metal oxide which can be reduced by carbon reduction process. And you already know about 3 amphoteric metals. I mentioned 3 of them, isn't it? What are the amphoteric metals? Aluminium, zinc, and lead. Okay, so you can think of any other. Okay, I think in the list is also given there. You see the options are given, no, in the question. It is not iron, it is not magnesium. Okay, because iron, magnesium are not amphoteric. It could be lead or aluminium, but it's not aluminium. Why? Because aluminium oxide cannot be reduced by carbon reduction process, because aluminium is quite a strong reducing agent itself. So the only option left in the given options there is lead. Sorry, I lead. So it is lead, which is amphoteric. So, and it's weakly electropositive. We can also reduce it by carbon reduction. But as per the plan, we had plan of extracting not by carbon reduction, by self reduction, but carbon reduction will also do. Okay. So that's it. Now the last part of 2017, the divalent metal whose oxide is reduced to metal. The divalent metal whose oxide is reduced to metal by electrolysis of fused salt. Okay, so you've got to find a divalent or bivalent, it means the same, something having valency 2. Which metal over there has valency 2? Options are given, no? Aluminium is not the right one, because aluminium is trivalent, its valency is 3. Sodium, aluminium, what's the valency? 3 is not a divalent metal. Sodium's valency is how much? It's 1, so it's not a divalent metal. Magnesium's valency is 2. Yeah, magnesium could be the one, because magnesium is the only metal over there in the option. Last option is potassium. Potassium is also monovalent, its valency is 1. So magnesium is the only divalent metal. And if you want to extract magnesium, you know magnesium lies almost at the top of the metal activity series, so it can be only extracted by electrolytic process, and that's what they're saying by the electrolysis of fused salt. So the answer is what? Answer is magnesium. Okay, so with that we completed 2017. So let's continue solving 2016. 2016. I don't know why this is too thick. Let's make 50% only. Yeah. 2016. First one. First question. Fill in the blanks from the choices given. Metals are good. Metals are what? There are options, no? Oxidizing agent or reducing agent? They are reducing agent. Metals lose electron and themselves they get oxidized but reduces others, isn't it? So the answer is reducing agent. I'm not going to write, so you just mark it. And why are they reducing agent? Because they are electron. Metals, what they do, they receive electron or they donate electron. They are electron donors, because metals lose electron because their ionization potential, that is energy required to remove electron, is very less. So with little bit of energy, they lose electron. That's why metals are donors. Okay, so the right option is donors. So that completes the first one. The second one, number two. Select the correct answer from capital A, B, C, and D. The two main metals in bronze are. Okay, so I told you you got to memorize the special property of alloys and their main components also. So bronze is an alloy of which important metals? Tell me. Bronze is an alloy of tin and copper. So copper and tin. The right option is D. Copper and zinc is which alloy? Copper and zinc is brass, isn't it? And copper is tin. Last option, the D option is correct, okay? Tin and copper. Yesterday we even talked about the special property of bronze. It is moldable, so you can cast into statues and different forms, you know. So that's a property that bronze has, and its main components are tin and copper. Number 3, identify the term. So the third one from 2016. Identify the term in the following. The main method to separate ore from gangue by preferential wetting. Okay. Now here, preferential wetting means what? Wetting means it's a process which uses lot of water. Okay. So in which method we have used a lot of water? You remember? Froth flotation, isn't it? We took water in a large tank and then added powdered sulfide ore and then added foaming agent, then passed a lot of gases. So because they're saying preferential wetting, so it is froth flotation. Now why it is known as preferential wetting then? Flotation. It's because uh, froth flotation is used for purification of sulfide ores, isn't it? And what is the reason why sulfide ores only? Because sulfide ores are extremely light, isn't it? They're extremely light. So they can attach to the froth that is being formed at the top of the water level. So okay. So in froth flotation process, the ore or the sulfide ore being extremely light gets attached to froth, you know, and the gangue, because it's heavy, goes to the bottom. So preferentially we only wet the sulfide ore that only rises to the bubble. That's the meaning of preferential wetting. Okay, so the process is nothing but froth flotation. Now number 4 from 2016. Name the solution used to react with bauxite. Now bauxite ore is purified by by a chemical leaching process called Bayes process, isn't it? Now which solution is used? Because bauxite ore is amphoteric, so it reacts with what? A strong base. So we use a concentrated solution of sodium hydroxide. You remember? It was heated at 150 degrees Celsius in Bayes process. So the solution used in the purification of bauxite ore is concentrated NaOH, and it's strong base. And this acts as a strong what? Base, and aluminum oxide acts as acid. So the answer is concentrated NaOH. Number 5. Number 5, oh no, not number 5. Number 4 has many options. So the second option of number 4, okay, from 2016. Write the equation for the reaction where the aluminum oxide for the electrolytic extraction of aluminum is obtained by heating aluminum hydroxide. You remember, this is the second time today we're discussing this reaction where aluminum hydroxide is heated. So what happens when aluminum hydroxide is heated? The second time. Where do we heat this? By the way, in the Bayes process of purification of bauxite ore, and the last step after the salt hydrolysis, aluminum hydroxide is formed, which is filtered out because it's insoluble and it's heated at 1100 degrees Celsius. Then it breaks to form aluminum oxide and water. So what do they want? They want you to write equation. So you can even balance this equation. Last time only I balanced. You just put 2 here and 3 there. The equation is balanced. So next one. Number 3 means third option from fourth question. Name the compound added to pure alumina to lower the fusion temperature during the electrolytic reduction of alumina. You know, in the extraction of aluminium from alumina, uh, we don't use only aluminum oxide because melting point is very high. So, which compound is added to lower the melting point? Basically, it is cryolite, isn't it? Na3Alf6. So, that's the compound that is added, cryolite. You can also say, because we are also adding calcium fluoride, so that is fluorspar, so you can say cryolite and fluorspar both, because again, if you don't write fluorspar, your teacher might deduct marks. Actually, they only want you to answer one compound that is being added, but you can mention both. But basically, remember, it is the cryolite which is used for lowering the melting point from 2050 to 950. Then write the equation for the reaction that occurs at the cathode during the extraction of aluminium by electrolysis. This you have already, today itself I wrote. Okay. So you just refer back to the previous. You may have copied, no? Earlier in this video only, I have discussed that reaction, and you have those both the reactions of cathode and anode written in your copy that you manage yourself. Okay. Explain why, last option. It is preferable to use a number of graphite electrode as anode instead of single electrode. You remember in the extraction of aluminum during electrolysis, we use several carbon or graphite electrode. Many electrodes were hung from the top, and I told you the reason why so many are used, because at the anode, which gas gets released? Oxygen, and oxygen at 950 is very corrosive, so it corrodes this electrodes, quite often. So we need to replace them again and again. So as we are replacing one of them, if you have used so many others, so others can continue the electrolysis, so electrolysis won't stop. So to continuously extract aluminium, many electrodes are added. As one gets replaced, others can still work. So that completes 2016. Now let's move to 2015. So what do you have in 2015? Choose from the list of, which is 2015. I think this is the 2015. Yeah, going back now. So 2015. Okay, 2015. Okay, so it is at the bottom. Select which is not the alloy of copper. So now again, I told you have to learn the composition of important alloys. So which is not an alloy of copper? Brass has copper in it. It's copper and zinc mixed together. Brass is that one. So it has copper. Bronze also has copper and tin. Solder metal. Even duralumin, though the main component of duralumin is magnesium and aluminium, but it has small amount of copper. The only alloy where the copper is not used is solder. And you know this solder alloy, it is made up of two metals, tin and what? Lead, isn't it? So this has no copper. So right answer is solder. Then next question, number 2 from 2015. Okay, so number 2 from 2015. Give scientific reason for zinc oxide can be reduced to zinc by using carbon monoxide, but aluminum oxide cannot be reduced. You see, last time when we planned the extraction of metals, I told you, like, aluminum oxide cannot be reduced by any reducing agent, cannot be reduced by carbon or cannot be reduced by carbon monoxide. The reason was aluminum is a very good metal. It's a strong electropositive metal. So being a strong electropositive metal, it's a good reducing agent. Yes, aluminum itself is a good reducing agent. And because these metals themselves are good reducing agent, so their oxide ore cannot be reduced by carbon or carbon monoxide. Okay. But zinc oxide can be reduced. Why? Because zinc lies below aluminium. Zinc and iron are moderately electropositive. So zinc oxide or iron oxide can be reduced by carbon reduction process. So you can reduce with carbon or using carbon monoxide. Remember, in carbon reduction process, you are supposed to heat those oxide ore with carbon or carbon monoxide. So when you heat with carbon, what happens? Carbon removes oxygen. So once oxygen is gone out of this, from here oxygen is gone, what is left? Zinc is only left, so zinc gets extracted. Carbon and oxygen forms carbon monoxide. Similarly, from iron oxide also, when oxygen is gone, it leaves iron. So this is how iron is extracted, and carbon and oxygen forms carbon monoxide. So I've given you the equation also of carbon reduction process using how carbon can be used for reduction of zinc oxide and iron oxide, but not aluminium oxide. Remember, this one's not possible because aluminium itself is a very stronger reducing agent compared to zinc and iron. Okay, so that's the reason why we don't use zinc oxide can be reduced, but carbon or using carbon monoxide, they're saying. Over here I used carbon. Okay, if it's using carbon monoxide, you just change this, you see, just turn this to carbon monoxide. Yeah, then if you use carbon monoxide, the other side there will be carbon dioxide form. Okay, so let me just change it so you can write like this. Yeah, what is next? From the oxide, so there are several oxides given. Okay, sulfur dioxide, silicon dioxide, aluminum oxide, magnesium oxide, carbon monoxide, sodium oxide. You have to select a basic oxide. Okay, what is a basic oxide? Basic oxides are metal oxide. So you have sodium oxide there. You see that for Na2, sodium is a good metal, no? So its oxide is what? Basic. So that's basic oxide. And what else you have to find? An amphoteric oxide. Out of that list, you see, the only oxide that I see as amphoteric is aluminium oxide. So this is amphoteric oxide, isn't it? Then what else we have? Any more option? No. Basic oxide, directly amphoteric oxide. Okay, that's it. Now last one. A metal X has valency 2 and a non-metal Y has valency 3. So it says there's a metal X, its valency is 2, and non-metal Y, and valency is 3. Okay, write an equation to show how Y forms ions. Write an equation to show how Y forms ions. Okay, so how Y forms ions. Remember, what is X labeled as? X is labeled as what? Metal. So X is a metal. And Y is a non-metal. So how Y forms ions? First, you see, Y is a non-metal. Non-metals, what do? They gain electron. How many electrons will gain? 3. Why? Because its valency is 3, no? Valency is given. And after gaining 3 electron, it becomes negatively charged, like this. So that's the equation which shows how Y forms ion. If they ask you how X forms ions, then X is a metal. Metals, what they do? Lose electron. How many? I think it'll lose 2 electron. Why? Because the valence is 2. So it'll form X plus 2 ion. But this is not asked. They want only the equation to show how Y forms ion. Okay. Yeah. Now, next, we are still continuing 2015. Next one. Describe the role played in the extraction of aluminium by each of the following substances listed. So that role we have already discussed, but still I think I can see some more new options. So in the extraction of aluminium, what is the role of cryolite? This I told you, cryolite, that is Na3Al(F6), is used to lower the melting point from 2050 degree to 950 melting point of electrolyte, isn't it? And also improves conductivity, improves conductance of the molten electrolyte. Okay, that's the role. And what is the role played by sodium hydroxide in the extraction of aluminium? What is the role of sodium hydroxide? Sodium hydroxide is exactly not used in the extraction, but it is used in the purification of bauxite, isn't it? So it is used in the purification of, so the role played by sodium hydroxide is that it is used in the purification of bauxite ore. And what does it do? Sodium hydroxide dissolves the ore because ore is amphoteric, isn't it? Purification of bauxite as it dissolves amphoteric ore. Dissolves amphoteric ore. Okay, that's the role. The last one. What is the role of graphite in the extraction of aluminum? It acts as what? Electrodes. You remember? Um, in the extraction of aluminium, the electrolytic cell was made up of iron. Yesterday you drew this, though. But inside the inside part of this is all lined by the tiles of graphite, isn't it? And what is this graphite doing there? Graphite is a non-metal, yet it is a good conductor of electricity. So it is used as an electrode, isn't it? This vessel itself was connected to negative electrode, so it acts as a cathode. And even the anode were also made up of carbon. That means they were also graphite. So the role of graphite is they act as what? Electrodes. So it is used as electrodes. Done. Done. Wonderful. Now, last one. Last one is, I think it's getting repeated again. Explain why in the electrolysis of alumina using Hall-Herold's process, the electrolyte is covered with powdered coke. So this you already know, you have already written why that powdered coke or charcoal is added on top of molten electrolyte. There were two reasons, yesterday you copied that. One is that oxygen involved at the anode is very corrosive, so that carbon is used, the charcoal powder is used to let oxygen burn that charcoal instead of burning the cell, the electrolytic cell. And it is also used as a heat insulator to maintain the electrolyte in molten state. So that one you have already done. So with that, we completed discussing everything. Okay. So I think the rest you can manage. So best of luck. Do it well.